In this little exercise, we're going to take some of what we learned about differentials and logarithms and see if we can't make some sense out of the meaning of this coefficient alpha 1. This is called a double log model because we have a logarithm on both the left and the right sides of the regression. We're going to look at semi-log models where only the left side is logged and only the right side is logged as well. If we begin by thinking about the meaning of alpha 1, we can write it down as the change in the log of y over the change in xi. I feel like this bothers some students. So for example, we could replace log of y with zi, and we could replace the log of x with wi. The model would become zi equals alpha 0 plus alpha 1 wi, and then there would be no confusion, right, about what alpha 1 was. Alpha 1 would be dz dw, okay, and we can just then substitute in for z log of y and substitute in for w log of x. And that's how we get at this expression right here, okay? So that's how we get to the writing of this particular expression, but what then does it mean? That's what we want to know. So I'm going to pick up on the single variate differential idea to answer that question. So if we think of a function of y as log of y, okay, and we then interpret this d log y literally as df, the total differential of f, okay, that is the change in f if we allow y to change. We know that that can be written as f prime of y dy, which is the derivative of the log of y with respect to y, 1 over y dy. And now we can interpret this. dy is a change in y. 1 over y is the rate of change of f with respect to y. When we multiply them together, we get the total change in the log of y when y is allowed to change by a little bit. But look carefully at this. If we have the change in y and we divide by y, change in y over y is almost a percent change. If we were to multiply that by 100, the change in y over y times 100 would be the percent change in y. Okay, so multiplying by 100, dy over y times 100 equals the percent change in y. All right, so let's go ahead and then try to interpret this. So what we're saying is, in the model, log of y equals alpha 0 plus alpha 1 log of x. Alpha 1 can be thought of as d log y over d log x. Okay, and we now have a story for what each of those means. That's dy over y divided by dx over x. Getting a little sloppy with my subscripts, but there it is. If I were to multiply the top by 100 and the bottom by 100, this would be the percent change in y over the percent change in x. Okay? That, we know, is in economics called an elasticity. Okay? So the interpretation of the coefficient alpha 1 is in fact simply the percent change in y over the percent change in x. We can extend this to multivariate context. Log yi equals alpha 0 plus alpha 1 x1i plus alpha 2 x2i. We would simply use the language of partial derivatives to write out what this meant. Actually, I'll tell you what, let's go ahead and get rid of that and start a new page. Log of yi equals alpha 0 plus alpha 1 log of x1i. I forgot the logs in the last one, that's why I wanted to rewrite it. Alpha 2 log of x2i. There we go. So we can write alpha 1 as the partial log yi over partial log x1i. And all that means is that we have the change in log y over the change in log x1i holding the x2 constant. We can interpret these in exactly the same way that we did in our previous model. This can be thought of as the change in y over y, the change in x1 over x1, okay? And it can be thought of as the percent change in y when there's a small percent change in x1 holding constant the x2 expression, okay? So what I want you to consider now is how we would interpret, using the same method. Now I'm purposefully omitting the log on the right hand side of the equation, and I'm going to omit the log on the left hand side. So I want you to think about for a while how to interpret these.